Function arithmetic. Another way to say function arithmetic is combine like terms, kind of, sometimes. So you can see here that we have the four basic operations with functions. Now what's going to happen is they're going to give us two functions. We just got to figure out if we got to add, subtract, multiply, and divide. They're going to tell us to in this format, okay? So, don't worry about this note here at the bottom, because this is just telling us, please don't make denominator 0, because if you do, it can jack things up really, really bad. So don't. But we can add functions together if they're different. We can subtract them if they're different, multiply them if they're different, and we can also divide them if they're different. Since we did see that division stuff, I'm assuming we're going to see some domain kind of stuff, which sounds exciting. So you'll see here that we got f plus g of 4. What you can do is you can actually operate with the functions, which is what I'm going to do here first. So f of g, so you see I'm ignoring the 4, right? So what I would want to find is just f plus g. And we can see here that the f function is x squared minus 7x. And then we're going to add that. So that's the plus sign between the two functions. But then we see that g is x plus 5, right? So that's just x plus 5. Like I was saying, at least with addition and subtraction of these types of functions, all it becomes is combining like terms. That's it. If it's multiplication, usually it's some form of distribution. So what I'm going to do then is I'm going to combine the two x terms. That's a 1x, by the way. So negative 7x's plus 1x's would be negative 6x's. And then I'm left with this. I'm going to say it's an expression, x squared minus 6x plus 5. This would be the function f plus g of x. But you'll notice down there at the bottom, or I guess to the left, it's f of g of 4. So from this new function that I found, which is f plus g, I just need to replace all the x's with 4s and then evaluate from there. So I'm going to take the x, both x's, and I'm going to replace them with the x value that they've given us, 4. Okay, so 16, that's negative 8 plus 5. I believe this is negative 3. So f plus g of 4 should be negative 3. Now, I purposely did the long way just because it makes the second way seem a lot easier. But if I show you the second way, which is the easier way, you usually hate it. And then if I show you a more difficult way, you just hate both of them. So there is some mental manipulation here. I apologize for doing that because it's, in my opinion, it's just propaganda. But here we go. Here's another way to do this. Is see how it's f with some kind of operation with g of 4. We can actually just find f of 4 and then g of 4 and then operate with these two, okay? Because if it says to subtract them, we could subtract those. If we wanted to multiply them, we could. If we wanted to divide them, we could. So I'm just going to find f of 4 first. So that'd be x squared minus 7. But of course, it's telling us the x value is 4. So I'm going to say we got a 4. 4 squared, 16, minus 7, 9, boom. So f of 4 equals the 9. Now g of x, which is, well, I say simply, but perhaps that's overemphasized there. But yeah, they're telling us that the x value is 4, so replace, crap. There we go. We're going to replace the x with 4. 4 plus 5, boom, still 9. So g of 4 equals 9. Well, if I had written that out right, if it was just the way I have it there, it would have worked. Dang it. Make sure you don't make that mistake. I'm okay showing my mistakes, by the way, because I hope you make some as well. That way we can learn from them. So hopefully you can learn from mine as well. And don't forget that x right there. We need that x. It's 4. Okay, so this should make a lot more sense. I say that because I looked at 9, and 9 plus 9 is 18, not negative 3. And that of course, didn't work because I made a mistake right here. So 16 minus 28, is that negative 12? Negative 12. And negative 12 plus 9 would be negative 3. Now it works. All right. The world is good again. Okay, so up here, let's do part B. I'm just going to drop it, though. F minus g of 4, well, this is just the f of 4, which is negative 12, minus g of 4, which is 9, and negative 12 minus 9, I get negative 21. Right there. So again, in my opinion, this is easier. Some students may say, yeah, Sal, that's not easier for me. And you're welcome to subtract the 2. Just make sure you use parentheses on the g if you do, and then work with it that way. But I like this way better. So next up, we got f times g of 4. Again, we do have the same, pretty much the same values throughout, right? It's just the operation is going to change. So that's going to be negative 12. That's the f of 4. And then the g of 4, which was 9, but the operation is now changed to multiplication. So this one should be negative 108. Oh, this one's going to give us a fraction. This next one, f divided by g of 4, which is going to equal, yeah, I guess we're dividing there, negative 12 and 9, which I believe equals negative 4/3. You're welcome to write the decimal there, but there's more 3's than I want to write on that one. Not because I hate 3's, but just because it's more writing than I want to do. So there we go. We had f plus g of 4, which is negative 3. F minus g of 4 is just negative 21. F times g is negative 108, and then f divided by g was negative 4/3. There's one quick step with the f minus g of x right here. Okay, so f minus g of x. So I'm going to take f of x, and I'm trying to use some technology to make this a little bit faster. We want that there. And then the g of x. Let's see if I can do this one. Okay, that seems okay. All right. This is going to take a lot of space too. Well, we're going to subtract these two, but you can't just put a subtraction sign between two functions like this. If you're going to do that, you have to put a parentheses around the second one because you actually need to change the signs of all the terms inside there. I actually look at it as though you're going to distribute negative 1. But it really is just changing the signs of each of the terms. So, right, like you could say, well, negative 1 times negative 10x to the power of 3 would be positive 10x to the power of 3. Negative 1 groups of negative 3x's would be positive 3x squareds. And then negative 1 times positive 9x would be negative 9x. And then also distribute to the negative 4, we'll just make it a plus 4. So you see it really just changed all the signs there. And then we still have the rest of it though. And now it becomes combining like terms, right? So what am I seeing here? We got not a lot of space. I see that I've got this 1x squared here, and then I've got 3x squareds there, so that'd be 4x squareds. Then I got x's, right? 7x's and negative 9x's would be negative 2x's. A constant 3 with a constant 4 would be positive 7. And then it looks like we just have this positive 10x cubed that just has to drop, so positive 10x cubed. I put it in this order just because I was seeing these from left to right, but it shouldn't matter which order you put these in. So f divided by g, I'm showing f of x, and then g of x divided by each other. I do not see a way to simplify these. So it's done. The next one here, f times g of x. I'm gonna consolidate some space here. So we got f of x. This one's gonna be so great. Times this g of x. I'll get rid of some of this other stuff so it looks pretty. These two, we're going to multiply. So I'm just going to put parentheses around that one. Well, you know what? I'm going to, here we go. I'm going to put some parentheses around the first one as well because we've got to multiply everything by each other. And by everything, I mean everything. After we do that, though, if this is consolation here, we have to combine like terms. So, I will definitely need more space, but I'm going to start with just what I have. I got to distribute this x squared into all four terms. And that's fun. So x squared times, I'm going to skip some steps just for the sake of time. X squared times negative 10x to the power of 3 is negative 10x to the power of 5. X squared times negative 3x squared would be negative 3x to the power of 4. X squared times 9x would be positive 9x cubed. Then x squared times negative 4 would be negative 4x squared. Wow, that was so fun. Let's do another one. Let's do the 7x as well. So I'm gonna multiply the 7x's by all the terms in the other set of parentheses. So that'd be 7x's times negative 10x cubed. That'd be negative 70x to the power of 4. And then we got 7x times negative 3x squared. So that'd be negative 21x to the power of 3. 7x's times 9x's would be positive 63x squared. And then 7x's times negative 4 would be negative 28x's. One more. Like I said, I definitely need more space there, though. Let's just kind of focus on this one. Well, I'll still zoom back out, though. Let's see if I can fit this. All right, but we got to show the 3 distributed. It's positive 3, so 3 times 3 times 3. So 3 times negative 10x cubed would be negative 30x cubed. I don't know if I can do it. 3 times negative 3x squared would be negative 9x squared. 3 times 9x's would be, 27x's. I'm so close. That'll do it. And then 3 groups of negative 4 would be negative 12. Yes. Now, as much work as that was, and as fun as it was, we're not done. Because like I said, now that we've done all the multiplication, now we must combine any like terms that we have. I see right off the bat that the negative 10x to the power 5 is just, there's no other x to the power 5s to combine it with, so it just stays the same. I now have a term, x to the power 4, right? So I see this x to the power 4, that's all that I see. Negative 3 of them minus 70 of them would give us negative 73 of those x to the power 4s. Gotta start mixing some colors here. Now we got x cubed, so x cubed, and x cubed. So that's 9 minus 21 minus 30. 51 minus 9 should be 42. Thank you. Negative 42 x cubes. And then we got some x squared, right? So negative 4, 63, and negative 9. So that'd be 59, 50. Positive 50 x squared. Now some, oh, we got, where was I at? Oh, we got this 27x here, which I don't see any other x terms. No, we do. There it is. See, there's a little bit of checking going on here. That's just going to be negative 1x, x's. And then finally, the negative 12 just drops. I don't see any other constants there. We also have this in what we call descending order, meaning the powers go down with each term. Maybe you wanted to know that, maybe you didn't. In any case, that right there, what we just barely did, going back to what we had from back here, that is f times g of x. And that was super fun. All right, the last one that we have right here is to take f of x and then add g of x, right? We did b, c, and d. But now we have to add the two. So I'm going to take these. I think I can fit them up there at the top. So I'm going to take f of x, and then I'm going to take g of x. Just kind of set it next to it there. And what I need to do is add the two together. Now I can put a plus sign right there. But if I want to, what I can just do is just make that minus 10x cubed and the rest of g of x. So when I solve this, or when I simplify it, it will give me f plus g of x. So that's what I will do now. I'm just looking for any like terms that I can combine. And I see that I have this 1x squared that I'm able to combine with this negative 3x squareds, which would give me negative 2x squareds. Then I also have these 7x's, which I can combine with those 9x's, which would be 16x's. And then 3 and negative 4, those are constants combined, would be negative 1. Last value I have here is this negative 10x cubed. I'm going to write this in descending order, although I do not believe that you have to do that. So this right here would be the final version of f plus g of x. So now that I have these, I now have all 4 of those answers. F plus g of x. This was f divided by g of x. I got that one. And then we also have f times g of x. And then we had f minus g of x here. So there's the 4 answers. And just to make sure we know, that's A, then B, then C, and D. So we found all 4 answers. All right, for this problem, we're going to evaluate these. And right here we can see we got f of 5 plus g of 3. I'm going to start with the addition right there. But we need to remember what f of 5 is. So I'm going to go to function f, which we can see is this function. I'm not worried about the table right now because my focus right now is just to find out what f of 5 is, right? So there's f of 5. I want to find out what this equals. But it's telling me that I'm trying to find the y value when right here, this tells me that x equals 5. So I need to find where x equals 5 on this graph, right? Which is right here. And then I come up here to this point on the graph, this one, which is showing me the ordered pair 5, 5. Okay, that means that the corresponding y value here is 5. And we can see that on the graph also, right here. So f of 5, that's the x is 5. We found the y value that corresponds with it. It also is 5. So down here, just from that individual value, remember I was pretty much ignoring everything else, f of 5 altogether is just the value 5. But next, it's showing g of 3, which is going to be in the table, right? So I come up here, and I say, well, what is g of 3? Well, in order to find g of 3, I need to know what the y value is if I can find where x is 3 in this table. And it's showing right here in this column. So x is 3, I go down and find my y value, which is 3. So g of 3 is 3 as well. Now again, that by the way, would be the ordered pair 3, 3. Perhaps we don't care about that, but this tells me here that my g of 3 is also 3. And again, these are the ordered pairs. That's 5, 5, 3, 3. The operation is showing as addition, so I will add those two, and I can see my total is 8. So f of 5 plus g of 3 is 8. Now I'm ready to go to the next problem. I have g of 2 minus f of 2. I'm sorry, I have g of 0 minus f of 2. So once again, I'm just going to start with g of 0. So I say, well, what is g of 0? Well, g of 0 is here, sorry. Because, again, this tells us the x value is 0, and it's telling us then to find the corresponding y value, which is 0. So g of 0 is 0. So where I have g of 0, I'm going to replace that with the number 0. But then it also tells me that I need to find f of 2. So I come over here, I say, well, what is f of 2? Again, this is asking for the y value when x equals 2. And we can find that from the graph. I just say, well, look, here's my x value that's 2. I come up and find the point that's on the line here, which is the ordered pair 2, 1. And its corresponding y value, well, it's shown in the ordered pair. It's also shown on this line that the y value is 1. Which, again, this would be the ordered pair 2, 1. So f of 2 is 1. So here in our original expression, g of 0 minus f of 2, I now have 0 minus 1, which if you need the calculator to do that, don't feel ashamed, but it should be negative 1. In fact, I'll write it up there. I'd feel better if it was right there. Now I need f of 5 times g of 0. We actually just found both, right? We know f of 5 is 5. And then we also saw that g of 0 is 0. Now some students say, well, how do you know there's multiplication? It's because it's not showing the multiplication between those two, and it doesn't have to, because multiplication is the only operation that does not have to be shown. So we really have 5 times 0, which overall, again, if you need the calculator to do that, don't feel ashamed of that. But the answer is 0. Next up, we have g of 3. So I'm gonna rewrite this, but g of 3 we know is 3. So I'm gonna take this g of 3, I'm gonna replace it with the value of 3, which is what it is, and then I can see just above this that f of 2 is 1. So that would be 3 over 1, which simplifies to 3. That'd be my answer. So we found all 4 answers there. We got 8, -1, 0, and 3. All right, interval notation, it shows the range of solutions. We see in this slide already. I just like to repost it because it makes me feel good. But remember, if you have the actual parentheses, the values on the tips are not included. Okay, if they are included, then we have to use the square brackets, which we can also demonstrate with either open or closed circles, respectively. We've seen this one before as well. So perhaps not this one. Domain error. In fractions, denominators cannot be 0. And usually what we will show is, well, I guess usually I like set builder notation because we can just declare what values don't work. In interval notation, we have to show what values do work, though, which means we have to figure out a way to take individual values out. That doesn't have to make a lot of sense right now, but hopefully it will. Now, with these, it says, what value for t is not in the domain of the function? Okay, if it's not in the domain, it would make the denominator, just like we saw on this last slide, it would make the denominator 0. Okay, so this also means that I don't care about the numerator. Just you can cross it out. It doesn't matter how big it is or small it is or negative it is. I don't care. All I care about is the denominator right here. So I'm looking at just 17 minus 20. What I know for sure is if it were to equal 0, bad things will happen, kind of. So I'm going to say it cannot. This symbol right here is telling us it cannot equal 0. It can never equal 0 because that would give us an undefined statement. And I can solve this just like I would an equation. So I'm going to find the value of t this way to see which value would not work. It's just when I drop this, it's not an equal sign, it's now it's a not equal sign. So first off, I'm going to isolate my t's by zeroing out that -20, so add 20 to both sides. So I can drop the 7t. This zeroes out, and 7t cannot equal 20. That's a good start. Next up, principle of equality still is a not equal sign, but now I'm going to divide both the sides by 7. I'll keep the fraction, by the way. So this is t, or 1t, cannot equal 27ths. So this means if you replace the t with 27ths, you would get 0 in the denominator, and then you'd have an undefined value. So everything else will work. This is the only value that will not work. But remember, this is just a statement. In the future, though, we need to figure out how to do this in interval notation, which I think you've seen. So on this problem, once again, I don't really care about the numerator. Some people like it to just scratch it out, right, like this. It does say that it wants the answer in not just set builder notation, but interval notation. So we're not just declaring, like the last problem, what values will not work. But it's important to know which values will not work. So I'm going to look at that denominator, x minus 5. And I know if it were equal to 0, that would be no good. So I need to make sure it does not equal 0. So there's my symbol for does not equal. And I can see pretty quick, I think some of you could do this in your head, but one principle of equality will do it to zero out that 5. And this will tell me what x cannot equal. So 0 plus 5 is 5. So 0 just cannot equal 5. I'm sorry, x cannot equal 5. And since I'm going to be looking to do this in set builder notation, I can actually use that does not equal in set builder notation, which looks like this. So fancy brackets x, you have a line there, and this reads x such that, now we need to make the statement, x cannot equal 5. Then we close it with fancy brackets. So again, the language here for the math is x such that x does not equal 5, and that would be set builder notation. So I'll box that part in for now. But we still need the interval notation. So how do we show in interval notation that 5 is not included in the interval? Well, when I do intervals, I like to see number lines like this, okay? Now, the number line would show that if you had the value 5, and I always like to show 0 on there just so I can make a relationship in positives and negatives, 5 cannot be included, which means that I'd have an open circle at 5. Anything else will work in terms of the domain. So that means everything to the left will work, everything to the right. In fact, I'll do that in a different color. Everything to the right will work. Okay, so just the green line right there, I would show with the interval. It goes all the way to negative infinity. It stops at 5, which is not included. So there's a open parentheses. Then I would unite this, starting again at 5, but not included. And this goes to infinity. This is a way in an interval that we can exclude values from, in this case, the domain. But this is the domain in both set builder notation and interval notation. Okay, so I think I talked about this just a little bit different in class, but I will make the point again, we don't care about the numerators. Even though they can be factored, and even though it's possible that you could perhaps make some phantom ones out of that, but I'm not concerned about that. The domain of f of x times g of x, we would be concerned, though, with at least the denominator of f of x, right? So that'd be negative x minus 1. Now, if you think about those two, functions, okay? So let me step back for a second, okay? In fact, let's go back here. So if I were to show f of x times g of x, all I would do is I would take f of x, which is this, and I would take g of x, which shows this, and then I would multiply these two together. Now, from here, it would be essentially fraction multiplication, but we still wouldn't worry about the numerators in terms of the domain, because that's all I'm looking for here is the domain. I don't really care about simplifying these. But what we end up with is we have the f denominator, the function f denominator, but we also have the g function denominator as well. Those two are being multiplied, and what we cannot have, this goes back to some 990 stuff, is I cannot have this be 0, and this would be a factor, and I cannot have this factor be a 0 either, because if they are, anything times 0 is 0, we cannot have zeros in the denominator. So what this allows me to do is it allows me to set up two different equations. I got negative x minus 1. I know it cannot equal 0. Okay, so and then in solving this, let's go and solve this. I'd say go and add 1 to both sides. So then negative, I'm going to show it as negative 1x cannot equal 1. But then divide both sides by negative 1 tells me that x cannot equal, in this case, well, negative 1. Okay, so negative 1 cannot be in the domain. Everything else can. And then also we have the g side of that, f of x times g of x. So that would be 2x minus 2. This also cannot equal 0. So from here, I would say, just like we did before, solve this like we would a system. No, not a system. I would solve it like an equation. I'm going to add 2 to both sides to zero that out, drop the 2x. Now cannot equal 2, then divide both sides by 2. So these almost look familiar, right? Because now I have x, it cannot equal 1. They are different answers though, okay? Now, just to emphasize what we just did right there, I found that x cannot equal 1, and I found that x cannot equal 1. It can't equal 1 because of this part of the overall function, f of x times g of x. Because if you say negative 1 plus minus 1, it really ends up being 1 minus 1, and then this denominator would be 0, and 0 times this would still be 0. You cannot have 0 in the denominator. So what about the 2x minus 2? Well, if you replace it with 1, 2 times 1 is 2, minus 2 is 0. Again, this would make this factor 0, and 0 times this, whatever it is, doesn't really matter. 0 times anything is 0, so we'd still have a 0 there. We cannot have zeros in the denominator, so we have found, then, that x cannot equal negative 1 or 1. So those values are excluded from the domain, right? Now I'm going to do this two ways because it didn't specify which way that it wanted. So let's go and do this in set builder notation. Okay, so I got my fancy brackets, x such that x cannot equal, and we have two values from here. We got the -1, I'll try to color code these, but also we have the blue 1. Okay, so these are the values that x cannot be. Which, I guess, that's the next part, right? Saying what the domain is all real numbers except, well, x equals -1 and also x equals 1. But I'm going to show this in interval notation. But for me, when I need interval notation, I like to have number lines. So I have 0, and then to the right would be 1, and to the left would be -1. Okay, now these values are not included, so I'd have an open circle at -1, and I would have an open circle also at 1, and then to the left, everything else to the left of -1 is good, everything between -1 and 1 is good, and then everything to the right of 1 is good. So these parts of the intervals, right, just the purple line, that would go from -infinity, stopping at -1, not included because it's an open circle. Then I would unite that, starting at -1 again, but still not included, going to 1, that's the green portion of the line, and then unite that, starting at 1, and this would go to infinity. It ran out of some space there, but still works. And that would be the domain in interval notation, but again, the unions there have excluded both -1 and 1, which is what it asks for down here, what values, the domain is all real numbers except these two here. So when you do this, remember, you get to ignore the numerators when you're finding these domains. In the future, we will want to factor and simplify them, but even then, we have to go back to the original denominators and determine what values will not work in the domain because we cannot have denominators be zeros. All right, find the domain of f of x divided by g of x. So it tells us down here the domain is all real numbers except, so we're just going to find the numbers that do not work, which is going to mean that any of the denominators cannot be 0, which includes f of x. Even though f of x is the full numerator of the full fraction, we still can't have a denominator in any case be a 0. So right off the bat here, now let me just show what this would look like if we were to work with it. So this would be f of x, and then would be dividing that by g of x, which looks like this. Okay, but again, I see that I have this denominator from f of x, that is -x minus 5. Okay, because any denominator cannot be 0. I need to make sure that is not equal 0. So I would solve this like I would a regular equation, add 5 to both sides, principles of equality, right? Drop your -x, that zeroes out. Negative x cannot equal 5, but then I would show that as -1. Divide both sides by -1, and you see that x cannot equal -5. So there's my first value that cannot be in the domain, -5. If x were -5, this denominator would be 0, and we can't have denominators that are 0 because they are undefined. The other denominator I see here is x plus 3, right? That came from g of x. So where g of x is x plus 3, it is in a denominator. That means it also cannot equal 0. So once again, solving this like a regular equation with principles of equality, I can drop my x. I've zeroed out the 3. So x cannot equal, in this case, 0 minus 3 is -3. So that would be the next value that I would have to exclude from the domain. So the domain, it can be any other number other than -5 and -3. Now, just based on what we did in the last problem, which I'm not going to do for the sake of time, you can think about what set builder notation would look like here, or you could also think about what the interval notation would look like. So this concludes 1.5. And if you have not completed the assignments, do those. Once you do those, you need to make sure to do the module quiz that goes with this as well before next class.